This video is about prime and composite numbers. This is one list of prime numbers. Notice prime numbers are, for the most part, odd numbers. The only even prime number is 2. The important thing to know about prime numbers is that if we were to make a factor tree for every prime number, we would only ever come up with 2 factors, 1 and the number itself. So the only 2 factors for 2 are 2 and 1. The only 2 factors for 3 are 3 and 1. The only 2 factors for 5 are 5 and 1. The only 2 factors for 7 are 7 and 1. So forth and so on. So what does that mean for composite numbers? Well, composite numbers are by definition not prime. That means they have more than those 2 factors, 1 and themselves. Let's look at the first composite number, 4. 4 is a composite because it has 3 factors. It has 4, 1, but it also has a factor of 2 because 2 times 2 is 4. Another composite would be 6. 6 has the factors of 6 and 1 still, but it also has 2 and 3. So 4 and 6 are composite numbers, which is different than our prime numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. Prime numbers go on forever, as do composite numbers. There are infinitely many of both. One of the main reasons we talk about prime and composite numbers is so that we can talk about how to simplify fractions. Because simplifying fractions, or you may have heard about it in the past as reducing fractions, requires knowing which numbers are composite, which numbers are prime, and what the factors of those numbers are. For example, 3/4. This is in simplest form. Now hopefully you've noticed that 3 is in fact a prime number, and 4 is a composite. And that's important to note when we're talking about simplifying fractions. The problem here is they don't share any factors. If they shared factors, there might be some simplifying we could do. But because 3 is prime and 4 is composite and they don't share any factors, there's no simplification available. Here again we have a fraction. 2 is prime. 4 is composite. But in this case, unlike 3 and 4, we actually do have factors that we share, because if we watch the factor tree of 2, the 2 factors are 2 and 1. And the factor tree of 4 is 2 and 2, and then each one of these breaks down to 2 and 1. So we know we share the factor of 2. Well, if that's true, we leave the 2 alone for a moment, but we can rewrite the 4 as 2 times 2. You agree that equals 4. In which case we can eliminate or divide out, if you will, one of the 2's, leaving us on top with, if it's not 2, it's 1, right? That's the other factor. And one of the 2's has been eliminated, so we're left with a 2 on the bottom. So simplifying 2/4 simplifies to 1/2. Why? Because 2 and 4 share a factor. If both numbers are prime, such as in 3/7, where 3 and 7 are both prime, it's very unlikely they're going to share a factor except in one case, when both those prime numbers are the same number. When they're the same number, that's the only time they share a factor. In that case, it simplifies to 1. So 3/3 is 1. 3/7, however, is in its simplest form. There's no shared factor that can be simplified together. There's no shared factor that can be eliminated. Now here's an instance where we actually have 2 composite numbers. 4 is composite and 9 is composite. But we call these numbers relatively prime. And relatively prime means that while they're not prime on their own right, they're prime in comparison to each other because they don't share any factors. 4's factors are 4, 2, and 1. 9's factors are 9, 3, and 1. Now you might say, but Mr. Huber, they share a factor of 1. Sure, everything shares a factor of 1, but that doesn't count because there's no simplification we can do. So in the case of 4 and 9, we call this relatively prime because 4 and 9 don't share any factors except for 1. Now here's a fraction that seems relatively complex, 140 over 350. What you want to notice is this can be simplified because these are both even numbers. And in fact, hopefully you've noticed that they both end in a 0. Now we know that multiples of 10 always end in zeros. So a way to quickly simplify this, and a trick you want to remember, is that if two numbers above each other on a fraction like this have zeros, you can eliminate the same number of zeros from each one. In this case, 1 0. If they'd had 2 zeros, we could have eliminated both zeros. If one has 1 0 and the other one has 2 zeros, we can still only eliminate 1 0 from each of them. Now we're no longer dealing with 140 over 350, but instead 14 over 35. And 14 over 35 is an easier fraction to reduce because we can do factor trees pretty quickly. 14 is 2 and 7. 35 is 5 and 7. And hopefully, again, you've noticed that they both share a 7, which means we can reduce that out of both numbers. We can divide that out. We can eliminate it. And if we divide 14 by 7, we're left with just the 2. If we divide 35 by 7, we're left with just the 5. So 140 divided by 350 as a fraction reduces all the way, or simplifies all the way, to 2/5. We did it a little bit just now. We did some multiplication, dividing, and fractions, but I'm just going to do a quick reminder on how this process works. It's something you've seen in previous years, but we all need a refresh after a summer, so let's talk about this briefly. Here's a multiplication problem, again dealing with two relatively prime fractions. And remember, with multiplication in fractions, all we have to do is multiply across the top and multiply across the bottom. So 11 times 8 is 88. And 10 times 5 is 50. And then we can check quickly if there's any simplification, and we recognize that there is, right? Because 88 and 50 are both even, which means they both have to share a factor of 2. So let's go ahead and just divide by 2 and see what happens. 88 divided by 2 is 44. 50 divided by 2 is 25. The factors of 25 are 1, 25, and 5. The factors of 44 are 4, 11, 2, 22, and 1. They don't share anything in common, so this is our final answer, 4/25. Now, in previous years, you may have been asked to turn this into a mixed number or some other form. I'm going to ask you to go ahead and leave it as an improper fraction. When dealing in algebra, improper fraction is actually the most convenient form to work in. So go ahead and leave your answers as improper fractions. That's fine. Here we have some fraction division. Now, you might remember back to the last slide and be thinking to yourself, hey, look, I've got some simplification going diagonally. Why don't I do that first? Well, it's important to note that you can't do that first. You can't do that first because that simplification there isn't available with division. It's only available with multiplication. Division, we have to start with fractions. We have to start actually by rewriting this in multiplication form. And to do that, we have to find the reciprocal. Now, the reciprocal is essentially a fraction inverted, flipped upside down. So the reciprocal of 10/3 is 3/10. And when we're changing division of fractions into multiplication of fractions, we actually want to find the reciprocal of that second fraction. So not the first one. The first one stays the same, 7/5. But the second fraction, we find the reciprocal of it, which again means flipping upside down, and we write it as 3/10. Now we can follow the same process we followed last time, which is multiply across top, multiply across the bottom, and we have 21/50. The factors of 21 are 3, 7, 1, and 21. The factors of 50 are 50, 1, 25, 2, 5, and 10. I think that's it. Yeah. So there's no other factors of 50. They don't share anything in common. So that's our final answer. Again, nothing needs to be done here. You can just leave it as 21/50.